All right, we're going to get started. So first off, sorry for the food being so late. But our first speaker is Justin Hughes. Justin received his BS and MS degrees in electrical engineering from the University of Illinois at Urbana-Champaign in 2010 and 2012. He's currently pursuing a PhD at the same institution under the guidance of Professor Alejandro Dominguez Garcia. Thank you.
Perfect Spanish.
His research interests include power system reliability, wind turbine modeling, and renewable energy integration.
Okay. Good afternoon. My name is Justin. Today I'm going to talk about thermostatically controlled loads, which basically means any kind of load that's controlled by a thermostat, and equivalent battery parameter identification. What that means is you can use these kinds of loads and aggregate them together and use them as a battery for frequency regulation, which is a valuable service for the grid. So I'd just like to introduce what frequency regulation is. This graph here kind of illustrates it. If you have a load like this green line, it's a little bit noisy over time, and it's variable. This blue line is the generation. It's a little more smooth. This is like the conventional generation tries to follow that load. But if you take the difference between the two, you end up with this red line, which is the noise. And we always want the generation to match the load instantaneously. So we need to kind of make up this power difference. The need for this frequency regulation is increasing because as we
Where is that plot from that you showed?
This is from an Oak Ridge paper. I don't know if it's real or simulated data. No. It's just an example to illustrate what it is.
It might come because I cannot see very well either, but I'm getting, I'm losing.
So as we integrate more renewables, wind and solar, they're uncertain, they're variable. This blue line, maybe gets kind of noisy too. Maybe we have some solar behind the meter, residential solar. That could make the green line more noisy. Basically, we end up with more of this frequency regulation, which is required. So it's becoming more and more valuable. The problem is conventional generation. A steam turbine can't change its output fast enough to follow that regulation signal. A combined cycle plant, maybe it can, but it's still not instantaneous. It has limits on its rate. Energy storage devices are becoming more common, and they're actually better able to track that. They can change their outputs very quickly. And recent changes, FERC Order 755 makes this, it's always been valuable, but they're going to be more and more rewarded for it now. This came out in 2011, and it allows payments to be increased to these types of devices which can more closely track the regulation signal. So flywheels, there's already a company that has flywheels, rotating masses for energy storage, and they're some of the people that lobbied for these changes. Chemical batteries, we've seen these installed at some wind farms right on site. We've heard people talking about using the batteries in electric vehicles during the day or at night. When it's just parked, it could be providing this service. What I'm going to talk about today is thermostatically controlled loads, and that could include, but not exclusively, air conditioners, water heaters, refrigerators, that kind of thing. Essentially, what defines them is they have some thermal energy storage, and they're controlled by a thermostat, meaning there's some set point. You say, hold it at this temperature, and there's some band around it, and the controller is going to keep the temperature in between those bands.
Do you believe that figure that 20% of the load at any point in time is TCL? It sounds very high. It says 1 out of every 5 megawatts is needed is for statically controlled load.
Where did you get that number from?
A peer-reviewed paper, Kameshwar's.
Kameshwar's paper, okay.
Yeah.
So I don't buy that number because even if we include with that air conditioning, because it might be that the energy that they consume 1/5 of the energy overall. That's possible over the whole year, but not in terms of at any point in time the load is going to be that much.
Okay, yeah, it could be energy, but regardless of the exact figure, it's pretty significant, right? Everyone has a refrigerator and heating and cooling. So.
Justin, I think you would say at any point in time it's probably not 20%. You're just talking about the average, right? Over
Sure.
the course of a year.
Sure.
Certainly on a hot summer day it might be higher. On a nice spring day it might be lower.
Right.
But you're saying 20% of the average is thermostatic control. George, you agree with that, right?
I do agree with that.
Yeah. So I mean, whether you want to define electricity as power or energy.
You're claiming at every point it's always
Yeah.
20%.
Yeah.
It's an incredible claim. 66%, 62% of the energy consumed in the country is by motors. That's true. But this is too high. It's definitely true in Washington, Oregon area because they heat that way.
Okay. Moving forward, I didn't come up with this idea. People have been exploring with it for quite a while. Here's a hot water heater that they have installed at the.
If the numbers come from Berkeley, question
them. This is installed at the PJM offices. It's a smart hot water heater. And if you were just to run this without any special control, like most of us probably have, it would cost $256 under certain assumptions to run every year. If you're looking at the locational marginal prices and you're heating it up when the electricity prices are low, like at night, you can cut those costs roughly in half. And if you additionally add this frequency regulation, the cost actually goes negative. They pay you to run this because the value of the service you're providing is actually more than the electricity cost. So pretty cool stuff. So let's.
Of course, if everybody does that, they've got a problem.
Yeah.
Incrementally, that's good.
Okay, so let's get into the math of how I'm actually modeling these. So I'm going to define temperatures as theta. So theta without a subscript is just the temperature inside the TCL. Theta A is the ambient temperature. Theta R is the reference or set point temperature. We have some input power. These parameters A and B here depend on the thermal capacitance and resistance. So basically, underlying this model, we're basically assumed that the ambient temperature is a voltage source, and the temperature of the TCL is a capacitor, and there's kind of a thermal resistor between the two. And this P kind of works out to be a current source.
How reasonable is that model?
So I'll get to that later. So far, I've seen that it's a good approximation to even complex loads, and I'm looking for kinds of loads where it doesn't hold so well.
I mean, I can see that working well for a box, right? I think we talked a little bit about what happens when you have more complex geometry. So you're going to talk about that? Okay, good.
So in this model, which is called the deadband model, there's a state variable Q. If Q is 1, it's on. There's some constant power being taken out. If Q equals 0, there's no power. You can't go in between. And the state persists if it's close to the reference within this deadband delta. But if it goes either too high or too low, it goes delta away from theta R, it changes state. It goes from 0 to 1 or 1 to 0. So this is maybe a more accurate model, but we can simplify this if we kind of neglect the controller. We just treat the input as kind of a continuous function that goes between somewhere between 0 and P. We call this the continuous model. There's just one first-order differential equation. Good. So I'd like to start by talking about how we can identify the parameters of this model, A, B, and theta A. So the method.
But you're going to say why that's required?
Not yet.
So you're just going to tell us that you're going to identify those parameters, and then later you tell us why?
Mm-hmm.
Right. I would do it the other way around, but that's fine. That's mistake. That's right.
So the technique I'm proposing is based on optimization techniques. This is advantageous. It can be done. All you need is it can just run like it normally would. You don't need any special control or anything. You record how much power it uses and what the temperature is, and then what you're trying to identify is A, B, and theta A. Theta A, maybe you want to identify it. Maybe you have a thermometer outside. You could add it or not include it, either way. So what we try to minimize the norm between this measured data and
Theta A, is that the ambient temperature?
yes.
No.
So you could measure it outside, but maybe that's not exactly right. Maybe you need an equivalent ambient temperature if you have neighbors.
Water heaters in their garage or something.
Yes. So maybe you need to identify that one too. So you might try to minimize the norm between the measured data and the prediction of your model. Your model is just the solution to this initial value problem. This is the same as before, and we start the initial condition at the measured time t equals 0.
If the power is going in, wouldn't the water be heating up?
So this is kind of built with an air conditioning load in mind. So theta A is going to be greater than theta R, and then the air conditioning cools it down. The same model would work for a water heater, but you need to flip some things around. So this is all nice and continuous. In practice, it's a little more difficult. This is sampled, and you need to use some numerical techniques to solve this. But the same idea, it can be used. But it's pretty inefficient to solve this, because to even evaluate the objective function, you need to solve for this initial value problem. You can't numerically calculate a Jacobian or Hessian. You have to approximate it. So it's pretty difficult. But it can be done. Here's some simulations. This blue line shows the result of the deadband model. I set the reference at 20 degrees and the deadband delta at 1 degree. So the controller is going to, so it starts off with the air conditioner off. It kind of warms up in the room. It gets to 21. It turns the air conditioner on and cools it down to here. And it just keeps going through that cycle.
Let me understand something. Go back one step. When you solve the ID problem, you assume you know theta and your power profile P, right?
Yes.
Yeah, okay.
And it should be easily measured.
Oh, correct. Yeah. So, but the P, the P that is being measured is like either 0 or 1. It's either 0 or total P, or total power going in. Either the thing is on or it's off.
Mm-hmm.
So the continuous model.
The continuous model there's no restriction that it has to be 0, 1.
I understand.
But
that.
in real life, yeah.
I understand that, but the way you're gonna use it, you are using the continuous model, but the data that you are feeding to the continuous model is either 0 power or it's like full power, right?
Mm-hmm.
So from that point of view, the continuous model is equivalent to the deadband model.
Yes.
Are we agreed?
Yes. As long as there's no noise.
All right.
Yes.
And theta A is assumed to be constant for the whole period?
Yes.
Why is that a good assumption?
Well, maybe you're working over a short enough time period, but that is a valid question. Yeah. So it's difficult to identify a time varying parameter. But anyway, if there's no noise and theta A is constant, we can identify this real well.
So Professor Rossi has pointed something out which I agree with him, which is 10 hours is not a short period, right?
Yeah.
For the temperature ambient to be.
But this is periodic. I'd get the exact same results if I went down to the period, which is 1 hour, which maybe it's reasonable.
But the important thing is the time constant of theta A changes with respect to the time constant of this model that you have.
Yeah.
Right.
And so if they're in the same time constant is okay, but I think the assumption of theta A being constant over the entire day, you have different air conditioning needs in the first hour of the morning than you have in the fifth hour, starting at 8 a.m.
Right, but the point is that if you are doing the ID over a very short window of time, let's say 10 minutes, which is all you need actually, because this is a very small model.
But then you have to do this kind of update all the time.
But I mean, in this case, since you're assuming that the structure is constant, my guess is that the A and the B will.
The A and the B should be the same, so that makes it easier. Yes.
All right.
Okay. So we're able to identify this pretty well.
Okay.
Now I'm getting to why I did this. If you just have a single load like this, it doesn't really make sense for this to participate in the market by itself. You know, if you're right here and it asks for more power, you're not going to be able to provide it because it's already at the limit. Plus, just the megawatts is real small. Really, you need an aggregator to put a whole bunch of these things together. So if you do that, and they're all perfectly identical, they have the exact same parameters for each of the loads, and you have a whole bunch of them, it reduces to this battery model, where X is a state, it's an energy value. And X equals 0 corresponds to all of the loads, are at the energy contained by the loads is exactly the same as if they were all at their reference point. So when it goes above or below 0 means there's the loads are at a higher or lower temperature than the reference point. Here, U is the difference between the power that they're actually consuming and the power that they would be consuming if there was no control. Because in steady state, in here, the power looks like kind of a square wave. When it's going down, it's 1. When it's off, it's 0. But if you have a whole bunch of them, they have a random phase shift. It kind of looks constant. U is the difference between what it actually is and that constant value.
So is that the same as the one you had before?
No, it's a different A.
Right.
No, maybe a notation problem.
There is a notation clash.
What's different? The A? Oh,
Yeah.
the A.
And there's some limits on this. You know, you can't make U whatever you want. There's going to be some charge and discharge limit, and there's a limit on the energy actually stored. It's always going to be between plus or minus C. That's the capacity of the battery. Like I said, if they're all the same, this is exact. If it's a heterogeneous collection, they have different parameters, then this model wouldn't be exact, but you can come up with a necessary model and a sufficient model, and the aggregate model is somewhere in between those two. And if the variation, if it's not too heterogeneous, you can get pretty tight bounds.
What does it mean? What does the necessary and sufficient model means in terms of the signals that they produce and the signals that the model that you have there actually produces?
So I think there's a technical way to say this, but I'm just going to say intuitively, I think it means that the performance is somewhere in between. So if you ask the actual end, when you ask for U, it will be able to meet some value. The actual value that it'll be able to give you is somewhere between the necessary and the sufficient values.
I don't understand why X doesn't say isn't the state.
X is the
State.
yeah.
Yeah.
And so why? What does it mean when I have negative energy? Negative state.
So I said X was the energy difference from the nominal energy, or the energy when all the loads are at their reference point.
Just subtracting a constant from it, nominal.
Yes.
So for all intents and purposes, I don't understand why you need an absolute value there.
Here. Well, it can go negative. Yeah. So it can go higher or lower, but it's going to tend to return to the reference point if you don't have any control.
So just think about it. So you need some. If you want to have like some reference temperature that requires some energy.
No.
What that model is capturing is how much the energy changes as the temperature is moving around that reference temperature. That's precisely what it's saying. And in fact, the energy is just some proportional constant times the some temperature difference. So that's essentially how it's defined. That's
I'm bothered by the fact that C is the capacity.
Mm-hmm.
Capacity is not the same units as energy.
Uh-huh.
Okay, and
No,
so
capacity is in energy. You have a battery at so many milliwatt hours. It's an energy.
capacity is megawatts. In power systems,
No, this is a battery, like a battery capacity.
it's called capability, energy capability, storage capability. Capability.
Where is Professor Craig? Let's not discuss. I mean, some of the power electronics guys, how do you call
No,
it?
they probably do call it capacity.
Yeah.
But I mean, this is a presentation of power systems.
Okay.
Okay.
Okay, so
We call capacity megawatts or kilowatts.
okay,
So it's capability.
out or
Capability is okay.
how about energy capacity?
Yeah.
Okay.
A generator has a capacity.
But that's the power.
Power capacity.
Yeah, it's power.
Okay, so that's
Okay.
what I'm trying to
So there's these parameters n minus n plus c. Assuming we do this identification procedure here, calculate A and B for each of the 1,000, hypothetically 1,000 that you've aggregated, then you can calculate what these are based on that 1,000 set of parameters. So that's one way to do it. But as I said before, doing that optimization is pretty difficult, and you have to do it for each load. So there's some drawbacks to that. So I'm going to propose a second technique.
Did you tell us already why you are doing this, baby?
To get the battery parameters, because when you're bidding into the market, you need to be able to say how much energy or power you'll be able to provide.
So essentially, you want to tell the aggregator how your battery model looks like, so they can use it.
Right. So the aggregator should understand what a battery is, but maybe they don't know what thermal resistances are. Yep. Okay. The second approach is to identify the battery parameters directly. And this is nice because it's real simple. You don't have to do that difficult optimization thing, and you don't assume anything that the underlying model follows that continuous model. The disadvantage is that you need to have the loads already aggregated, you need to have a controller, and that's the disadvantages. The controller uses feedback to turn the units on or off to meet the regulation signal. So the controller decides what U is based on the regulation signal, and the ones, so if it's too high, it needs to turn some off. What it does is picks the ones that we're going to turn off anyway, and then it works its way up. So it's a priority-based controller. So here's an example. I put together 1,000 loads. I give it some regulation signal, and the controller actually works real well. The power deviation follows that regulation signal. Now, this works real nice if you have everything within the limits, if no limits are violated. If you do violate some limits, it won't be able to follow it. But if you just run like this, you also won't be able to figure out what the limits are. So you need to give it some real extreme tests to kind of figure out what the limits are. So here I've given it a value that's way below what it can actually give. So maybe it can actually give minus 2 megawatts. That's what we can identify when we tell it to give us minus 5. So we just record what the minimum value here and the maximum value here is, and that gives us n minus and n plus. Not too hard. The next thing I'm going to look at is the capacity. In this case, we give it a regulation signal that's within its limits, and it's going to follow it for some time, but eventually, it's a battery, it's going to run out of energy, so it falls down here and unable to provide it. So to find the capacity, we just integrate this area, and it'll give you a megawatt hour value, and that's the capacity of the battery. Once it's down here and failing to meet the requirements, that's when all of the units are at the edge of their dead band, and you can't really get any more energy out of it. And what the controller is doing is they turn on for just a second and it turns them off. So it's doing this frequent cycling. It's not something that you want to do. So that's a drawback of this technique. Finally, we need to figure out what A is. We do this by finding the signal, the largest signal U that the system can meet in steady state, because in steady state, x dot equals to 0. We know U equals AX. The dissipation will be the biggest when x is at its capacity. So we can calculate A as Umax over C. We've already calculated C. So this, here I've given a regulation signal that's constant, and it manages to meet it. I go 1% higher, and you can see it starts to fail to meet it at certain times. So I know this is Umax here, and then I can calculate A. And I haven't shown the values, but what I actually found from doing this study is it matched real nicely with what I calculated using the other way. So I kind of over my time, but Alejandro wanted to know, what about more complex loads? What if we're not actually, what if the underlying loads don't have that first order model, the continuous or deadband model? So I worked with some mechanical engineering graduate students. They have this toolbox called Thermosys. I was able to put together a very complicated model of a refrigeration system. It involves these components. But really the only states that I care about are still the power and the temperature. So I ran the simulation. I got this blue temperature and power. You can see there's something higher order going on there than what we'd seen before. But it turns out when I run the identification procedure, my first order model can still represent it very well. So this tells me that maybe the AC dynamics aren't that important. Maybe we can just use the first order model to represent some complicated air conditioner system.
Are the time constants real short in that detailed model? I mean, it looks like you got fast dynamics there.
I think that's what it is. Compared to the thermodynamic kind of load, the thermal capacity, it's much smaller.
So what power are you
So you could probably do a formal singular perturbation if you had all that 13 equations.
So what power are you using here in the ID? The reference to the compressor or the electrical power out of the compressor? Or the electrical power that the compressor is consuming?
Yeah, so this is actually the power into the compressor divided by some efficiency. So that's assumed to be the input to the motor.
Okay, fine.
Yeah.
Very good.
So it's proposed that this second technique here is good for situations where the first technique doesn't work so well. I've shown that the first technique does kind of work well here. What I'm hypothesizing is that for a more complex building, maybe kind of a commercial supermarket or an office building or something like that, that would have more complex dynamics on the time scale of this, and we would require that first technique wouldn't work because of its reliance on those underlying assumptions. And I'm currently working on that.
So how do you look at that? Could we talk a little bit about that?
Yeah, so I have done that, and so far just a second order model where you have like a house with you regulate the temperature inside, and you have an attic with a whole bunch of hot air in it, and that's a second order model, and that also works to be a first order model real well.
Did you identify that already?
Mm-hmm.
Very nice. I'm very impressed. So essentially, you just build an RC circuit. Actually.
Second order RC circuit, yes.
So in practice, we could actually just generalize that to, if you have like different spaces, you assign like a state to each of those spaces, and then there is going to be some coupling, but at the end of the day, it's just a linear system.
Yeah. I mean, maybe if you have a varying theta A or something, those second order effects would come into play, but so far I haven't seen it.
Right. But I mean, you were able to identify the second order model.
Mm-hmm.
Nice. Okay, cool.
Okay, that's it.
What were your constants for the second order model and the first order model? Because I can see that, like in any complex system, if all the time constants are similar,
Yeah.
you can replace it with one. But if there's varying time constants, you're going to see really poor average.
Yeah. So I mean, I was designing a square house with a triangular roof, and you assume that the energy is being stored in the air, right? So the thermal capacitance should be proportional to the volume of that. So I made the area of the roof like a third or something.
So you say the thermal resistance inside the house, outside the house, inside the house.
So thermal capacitance is proportional to the area, and then I made some rough approximations on thermal resistance, which is like the insulation of the walls, and yeah. And I don't know how accurate those are. That was just me. I couldn't find any published papers that had like good values for that.
I have one more question. So, it's like your supermarket example. So, would they just say we have all these compressors on like the refrigerators?
Mm-hmm.
They would want to first find capacity by turning them all on and turning them all off.
Mm-hmm.
Is that the process they go through?
Yeah. So it's proposed that maybe they wouldn't want to do that, or even if just residential, you wouldn't want to actually do this on the real grid. So maybe you could come up with a detailed model and then run the same technique on the model of it rather than the actual system. Yeah, and that would go away with, like, they don't want to accidentally melt all their food or something.
Because we are running a bit behind, I'm going to ask you guys, unless you have really pertinent questions or urgent questions, to hold them until the end and ask Justin offline. So let's thank Justin. Our second speaker is Yue Tao. He got his BS in 2011 from the University of Tennessee, Knoxville, with honors in electrical engineering and a double major in math. He got his MS in 2013 in electrical engineering with Professor Krein doing work on hybrid power systems for mobile refrigeration applications. And now he's a PhD candidate with Professor Krein, possibly working on energy efficient buildings.
So Justin talked about mathematical model of a battery. I want to cover the basics, especially industry-related topics. Last week I thought I wanted to do a presentation on both industry and research, which including modeling and simulation techniques. But I made these slides very long, and all right, I'll just no, cue it. All right. So I did a lot of background research on battery stuff, and so this presentation will be about that, especially on automotive industry, battery electric vehicles, not so much on the grid level. I want to start with these two pictures. The first one is the Tesla Model S, which was on fire 2 weeks ago in Nashville, Tennessee. And the third fire, yes, third fire this year, I think. And not only it's a technical problem, it's also a financial problem. Tesla stock dropped from 180 per share to 120 today. So that was recent, yes. So it has a lot of impact on the society. And also earlier this year, it has the Boeing 787 battery issue. It's also burned like this. So this is a problem to us, and also it's a motivation to work on making it better. Agenda for today is this. I want to cover battery basics, compare between several battery chemistries, dive into particularly lithium-ion batteries and its physical construction and its performance characterization. And later, I think pretty useful is safety issues and test standards. These are all pretty industry related topics. This is the first battery known, first known source of constant current. It is built on a stack of zinc and copper cells, and inside is just brine soaked, which is seawater soaked cloth, and it can form a current. How does a battery work? Maybe you have heard about this before. It's basically a redox reaction. The cathode side and anode side, cathode is positive, anode is negative, and there's ions moving between and form this electron path. What is the battery voltage? Battery voltage is driving force across the battery terminal. It defines how many joules per work per coulomb of stored energy, stored charge. Some of the industry terms, primary cells are usually mean the one-time use, and the secondary cells are the rechargeables. So we focus on secondary cells today, which are mostly lead acid and nickel, blah blah blah. Lithium polymer is a new technology of the lithium ion. The difference is the lithium polymer has a solid electrolyte instead of a liquid. It has more flexibility when we want to construct it. And we want to compare a few of the battery types. So cycle life, nickel, cadmium, and lithium ion phosphate are the best. Charging wise, this one, and also this one. Overcharge tolerant, lithium ion is pretty good. Self-discharge, lead acid, lithium ion. Cell voltage, lithium has the highest, which is usually from 3.3 volt to 4.2 volt. So this is a nominal range. Lithium ion also handles more current. The C means, for example, we'll have a 2 amp hour battery. The C rating 20, for example, 10 C means I can handle 10 times 2, 20 amp. Okay. Temperature, blah blah blah. Safety. Okay. I have a lot of slides, so I want to go through quickly since last one is. Huh?
How many slides?
About 40. But they are not mathematical, so just go through them. Yeah, we have time. I think I practiced this. I only spent 5 minutes so far, so we're. All right. Advantage of lithium ion. These just want to read yourself. The problem is safety and also energy storage and how energy density. One of the biggest challenges in automotive industry now is can I store enough energy for the lithium ion and also charge fast enough. Theory of operation, how it works. So on the anode side, it's basically graphite. Cathode side is lithium combined with some metal oxy something. There's a copper collector and aluminum collector on the cathode side. Some of chemistry here, just for your information. Basically, lithium ion goes out and also release some electrons. Similar for the negative, it's a carbon basically. Overall, it's lithium plus carbon. This is an interesting picture. This is an unfolded lithium-ion battery. This is a positive electrode, negative, and the separator. Separator is a very important one. It is a polymer essentially, and it provides insulation, but also provides a channel for the ions to communicate. This is a cross section of a cut cell, and zoom in here in the micrometer scale. Cathode is basically lithium, and anode is graphite. And collectors, the separator is just this thin layer here, which is about like 20 micrometer thick. There are a few types of lithium-ion batteries. One is the cylindrical, it's like this. So it's like wrapped around many layers inside to provide that energy storage. There are several smart things in here. One is the PTC device, which is a positive thermal coefficient device. It means if there's over temperature inside, that one will automatically trigger and prevent that failure. And the vent is if the air pressure inside is too high, the vent provides a mechanical release of the air. And the current interrupt device is another protection device for the air pressure. If air pressure is too high, it's electrically open circuit the battery. And others I have covered before, right? Okay. And prismatic, another shape, it's more flat, this kind of shape. And the stacked polymer, just several different shapes, similar physical construction. There are several cell characterization here. One is ray gun. I don't know if that's the right way. Ray gun analysis. It's basically plotted discharge power versus discharge energy for the cells. This is interesting picture. On the vertical axis, it shows energy storage, which means the range of a vehicle, and horizontal is the acceleration and also power. Lithium-ion is pretty out, so that's good, but still want to increase this, push it even further. Huh?
What does the word dragon mean?
It's just a name, I think. Yeah, it's basically just analysis involving plotting the discharge power versus
the name of the guy who did this first time?
I didn't do research on this. I can look it up for you later. Yeah. Reference electrode testing. It's testing of individual cells, especially the voltage at the voltage level of individual cells. These are a few things we need to characterize when we define a battery. And also calendar life testing, how long you can go through, and aging issues and all that. Just real quickly. This one is cell voltage versus the state of charge. Charge from 0 to 100%. The overall voltage is it's increasing a little bit, and that one is the difference. It says it's the difference between the yellow and the green, which is the cathode and anode. Typical charging profile is like this. The horizontal is hours, and voltage behaves like this, and yeah, you can see the charge current is flat first and then decrease. Next is battery management systems. How the battery is monitored and controlled inside the electric vehicle. This path is the charging path. You take a charger and go through the protection circuit and go into lithium-ion and backwards to the motor drives. So, and this one is overall picture of a hybrid electric battery system. Battery is here, and here's a high power part, provides power to the motor and the converter. And this part is the communication and the low power side, which controls the batteries and the monitor. And next is safety. Huh? Where's the source? I have the source. I didn't put it on there. Yeah, I should. Yeah, I realized. But there's so many pictures.
Government secret?
If I can find it, probably not. Next is the safety issues. They catch on fire when they fail. So different levels of failure. The reason behind failure is the thermal runaway. This is the term you want to remember, thermal runaway. So this is an experiment done, some paper from Florida. And the short circuit is a negative electrode, and notice the temperature just goes up like in the 20 minutes range, and eventually the separator, that thin layer melts, and it creates a short circuit path. And from that point, the temperatures go up very quickly. And this point means it fails, and probably catch on fire and drop down.
What kind of protection schemes can be developed against that?
I'm going to talk about that soon. Yeah, like how are we going to test on the safety issues? Yeah, there are several causes. We want to identify the causes. Actually, I talked about that earlier. You were not here. There's a protection device on the battery.
But you have copies, right, of the presentation called 95 plus about shipping and handling.
All right, so there are several causes. We want to identify the causes first. They're mechanical problem, electrical or thermal, and also cell internal. Mechanical means actual force or shock. Electrical means overcharge short circuit. Thermal is over temperature. Cell internal means some contamination inside the metal and the construction. So there's a vent that releases air, and the flame and the content release failure. The most obvious one is external short circuit. This is easy. You just connect the positive and the negative with the wire, and it's the external short circuit. But the internal short circuits are important to know. There are several causes here, which contains metallic contamination, dendrite growth. I'll talk about that later. Lithium plating, which means the lithium deposits on the graphite plates. Charging outside rated temperature, separator failure, mechanical abuse, improper charging protocols. Cell defects, as I said earlier, means probably some contamination inside the cell and during the manufacturing. Overcharge is an issue. If you overcharge too quickly, this one shows the overcharge 1C. Temperature is like this. 2C is way high there. So that's another cause. Overdischarge can result in oxidation of a copper current collector on negative electrode, leading to copper dissolution into electrolyte. So if you over-discharge very frequently, the life just reduces rapidly. High voltage issues. Lithium-ion batteries inside the HEV are usually very high voltage, 160 volt or higher. UL defines excessive 60 volt as hazardous, and it can be also arcing problem, which causes extreme high temperature. Next few slides talk about testing standards. These are a few standards in industry usually follow. UL, IEEE, NC, UN, these are some big ones. One of them I want to just dive into a little bit. So it's a very comprehensive testing procedure. These are all the tests they need to perform in order to get certified. Mechanical test and environmental test, all this under one UL number. Two kind of illustration of how they do the test. One is to remove the coating on one of the metal material, so therefore create a short circuit path, and they can test the behavior from that point. And this one is a sort of a stress test. They use these two balls, kind of pinch, and to create a mechanical stress, eventually a short circuit path, and monitor the outcome. What we have covered today are these, and that concludes my presentation. Failure reason?
Yeah.
I think, yes, I think on the news it says he hit something, and I think, is that right? Do you know?
Responders are told to,
You mean for
Tesla,
Tesla?
Yeah.
I don't think they know exactly.
Right, not conclusive yet. Yeah.
Because I think they're extremely scared about releasing any information so far.
Right.
I mean, it cost Boeing billions of dollars
Mm-hmm.
to get that plane started.
Right. Right. So it's not conclusive yet, but it's one of those reasons. I think probably it's a mechanical hit something or I'm not too sure. For the Boeing battery, it's also not released that information, the cause. But some rumors online says probably battery management system goes wrong.
So as soon as that happened, Washington sent to the group of people to do the investigation because this is such a big issue.
Right.
Very, very big issue.
Right.
So I think it would be interesting if one of the guys in the group could do a seminar about the safety issues because they'll really, I think it's going to be a killer in terms of trying to get this market started. Nobody wants to buy
Yeah.
a living vehicle which goes up in smoke.
Right.
There's also a really big difference between handling a bunch of people that have a problem on the road and handling regular people on the road. Like the first responders have to relearn how to respond to people. So I think that's something that needs changing as well.
Okay. And actually on the abstract, I mentioned something about modeling, simulation of a battery model for electric vehicle. I'll advertise this for next seminar, next semester maybe, which I may talk about. That's more mathematical intensive and related to research. It's more research. This is.
We need a whole semester to prepare for that. Is that what you're saying?
No. This is. No. It's only part of my research duty. I'm now on another project actually. So, yeah. Anything else? All right.
Aaron has sent out please do that because we're counting on you guys to make that stuff. So let's sign up with all of them. So if you can't, if it's a new different, just send it back to us with anything else. Like this is like I'm not. I don't have that.